Brought to you by WikiVidi.com. 1257 Samalas eruption. The 1257 Samalas eruption was a major volcanic eruption of the Samalas volcano next to Mount Rinjani on the island of Lombok, Indonesia. It left a large caldera next to Rinjani volcano, the lake Segara Anak. This volcanic eruption reached a volcanic explosivity index of 7, making it one of the largest eruptions of the Holocene. The occurrence of this eruption was originally deduced from ice core information revealing a spike in sulfate deposition around the year 1257. In 2013, the source of this eruption at Samalas was definitively proven as a result of historical records from that time. This eruption proceeded during 4 distinct phases, alternately creating eruption columns reaching up for tens of kilometers, and pyroclastic flows that buried large parts of Lombok, destroying human habitations including the city of Pamatan. Ash from the eruption fell as far as Java. The volume of the deposits left exceeds 10 cubic kilometers. Later activity from the volcano created additional volcanic centers in the caldera, including the present-day active Barudari cone. The eruption was witnessed by humans on Lombok, who recorded its effects on text written on palm leaves which were tied together to make a book named Babad Lombok, which is the source for the mountain name, Samalas. The aerosols injected by the volcano into the atmosphere reduced the solar radiation reaching the surface of the Earth, triggering a volcanic winter and cooling lasting for several years. It is possible that the 1257 Samalas eruption helped trigger the Little Ice Age. General geology. Samalas and Mount Rinjani are in the Sunda Arca subduction zone, where the Australian plate subducts beneath the Eurasian plate. The magmas feeding Samalas and Rinjani probably form from peridotite in the mantle wedge beneath Lombok. Other volcanoes in the region are Agung Batur and Bratan on Bali west of Lombok. Before the eruption, Samalas may have been 4,200 plus or minus high based on reconstructions such as continuing upwards its surviving lower slopes. The oldest geological units on Lombok are late Oligocene, before 12,000 BP. Volcanic activity built up the Samalas volcano during a phase between 11,940 plus or minus 40 and 2,550 plus or minus 50 BP, where the Rinjani volcano formed. This last eruption generated the Rinjani pumice, with a volume of 0.3 cubic kilometers dense rock equivalent. Another eruption took place between 5,990 plus or minus 50 and 2,550 plus or minus 50 BP, forming the Propok pumice with a dense rock equivalent volume of 0.1 cubic kilometers. More eruptions are dated 11,980 plus or minus 40, 11,940 plus or minus 40, and 6,250 plus or minus 40 BP. Then, a large caldera-forming eruption destroyed Samalas volcano. Later volcanic activity occurred in the Segara Anak caldera, forming the Segara Anak Rombogan and Barudari volcanoes. Of these, most volcanic activity occurs in the Barudari volcano, with eruptions in 1884, 1904, 1906, 1909, 1915, 1966, 1994, 2004 and 2009. Rombogan was active in 1944. Volcanic activity mostly consists of explosive eruptions and ash flows. The rocks of the volcano are mostly dacitic. Contents range between 60–63% by weight. Volcanic rocks in the Banda Arc are mostly calc-alkaline, ranging from basalt over andesite to dacity. The volcano rests on crust of about 20 km thickness. and the lower extremity of the Wadati Benioff zone is about 164 kilometers deep. Eruption. The eruption of 1257 occurred probably around September. Based on the deposits of the eruption, it commenced with a first phreatic stage that deposited 3 centimeters of ash over 400 square kilometers of northwest Lombok. In the subsequent first magmatic stage, a lithic-rich pumice ash fell, reaching a thickness of 8 centimeters both upwind on East Lombok and on Bali. Subsequently, various phases of lapilli and ash falls occurred, as well as pyroclastic flows that were partially confined within the valleys on Samalas' western flank. Some ash deposits were eroded by the pyroclastic flows, generating furrow structures. Pyroclastic flows even crossed the Bali Sea, reaching the Gili Islands. This eruption phase was probably phreatomagmatic, as the deposits show evidence of interaction with water. 3 pumice fallouts subsequently fell, reaching the widest extent of all deposits formed by the eruption. These pumices fell as far as Sumbawa in the east, where they were up to 7 centimeters thick. The formation of these pumices was followed by another stage of pyroclastic flow activity, probably caused by the collapse of the eruption column, and the beginning of the formation of the caldera, where the conditions changed from column generating to fountain generating. These pyroclastic flows were deflected by older volcanic edifices and incinerated the vegetation. Interaction between these flows and the air triggered the formation of additional eruption clouds and secondary pyroclastic flows, where the flows entered the sea north and east of Lombok. Steam explosions generated pumice cones on the beach and additional secondary pyroclastic flows. These pyroclastic flows had an on-land volume of 29 cubic kilometers and reached thicknesses of 35 meters as far as 25 kilometers away from Samalas. These phases are also known as P1, P2, P3, and P4. The whole eruption lasted between 12 and 15 hours, not accounting for the first emission of pyroclastic flows. Tephra from the eruption fell as far as Java, forming part of the so-called Muntilan tephras. In Lake Logung on Java it was 3 centimeters thick. On Agung volcano on Bali, the deposits reached thicknesses of 12. Most of the tephra was deposited west-southwest of Samalas. Considering the thickness of Samalas tephras found at Mount Merapi, the total volume may have reached 32. The dispersal index of the eruption reached 7,500 square kilometers during the first stage and of 110,500 square kilometers during the third stage, implying a Plinian eruption and an ultraplinian eruption respectively. The eruption column from this eruption reached a height of 39 at wind speeds of 10 meters per second during the first stage, and 43 between the 2 stages, with emission of pyroclastic flows. This eruption column from was high enough that in it and its isotope ratio was influenced by photolysis. At high altitudes, various volumes have been estimated for the various stages of the Samalas eruption. The first stage reached a volume of 12.6. The second phreatomagmatic phase has been estimated to have had a volume of 0.9. The total dense rock equivalent volume of the whole eruption is at least 40 cubic kilometers. The material erupted by the volcano had a temperature of about 1000 C compositionally. The material was of tracheodacitic composition containing amphibole apatite clinopyroxene, iron sulfide, orthopyroxene, plagioclase and titanomagnetite. It formed out of basaltic magma, by fractional crystallization. The eruption has a volcanic explosivity index of 7, making it one of the largest eruptions of the Holocene. It was even stronger than the eruptions of Tambora in 1815 and Krakatau in 1883. Other eruptions of comparable intensity are the Coral Lake eruption in the 7th millennium BC, the Mount Mazama eruption in the 6th millennium, the Minoan eruption, and the Tierra Blanca Jovan eruption of Ilopango in the 6th century. Pumice Falls, with a fine graining and color of cream, from the Samalas eruption form a useful tephrochronological WIKT marker on Bali. Tephra from the volcano was found in ice cores as far as 13,500 kilometers away from Samalas. The eruption left the Segara Anak caldera, which has a diameter of 6, where the Samalas mountain was before. Within its 700 high walls a 200 meters deep crater lake formed. The Barudari cone rises 320 meters above the water of the lake and has had 15 eruptions since 1847. A crater lake may have already existed on Samalas before the eruption, and supplied its phreatomagmatic phase with 0.1 of water, or the water came from aquifers. A collapsed structure cuts into Rinjani slopes facing the Samalas caldera. The eruption that formed the caldera was first recognized in 2003. And in 2004 a volume of 10 cubic kilometers was attributed to this eruption. Early research considered that the caldera-forming eruption occurred between 1210 and 1300. In 2013 Levine suggested that the eruption occurred in May–October 1257, resulting in the climate changes of 1258. Research history. A major volcanic event in 1257–1258 was identified from data in ice cores and from medieval records in the Northern Hemisphere. The sulfur deposits in the polar ice caps had already showed that climate disturbances reported in that time were due to a volcanic event, with the global spread indicating a tropical volcano as the cause, although at first a source in a volcano near Greenland had been considered. The spike in sulfate concentrations was first observed in the Crete ice core associated with a deposition of rhyolitic ash. These ice cores indicated a large sulfate spike around 1257, the largest in 7,000 years and twice the size of the 1815 eruption of Tambora sulfate spike. But later discovered sulfate spikes around 44 BC and 426 BC rival its size. This discovery was made in the 1980s. In 2003, a dense rock equivalent volume of 200 was estimated for this eruption. But it was also proposed that the eruption might have been somewhat smaller and enriched in sulfur. The volcano responsible could not be identified at first. Tofu, a volcano in Tonga, was proposed at first but dismissed as the Tofu eruption was too small to generate the 1257 sulfate spikes. Likewise, a volcanic eruption in 1256 at Harat al-Rahat near Medina was too small to trigger these events. Other proposals included several simultaneous eruptions. Estimated caldera diameters ranged 10. The suggestion that Samalas, Rinjani might be the source volcano was first made in 2012. Since the other candidate volcanoes El Chichon and Quilita did not match the chemistry of the sulfur spikes, El Chichon and Quilita and Ocotina were also inconsistent with the timespan and size of the eruption. The conclusive link between these events and an eruption of Samalas was made in 2013 on the basis of historical records in Indonesia. The Babad Lombok writings in Old Javanese on palm leaves written in the 13th century induced Frank Levine, who had already suspected that a volcano on Lombok may be responsible, to conclude that the Samalas volcano was responsible. This event occurred before the end of the 13th century. The role of the Samalas eruption in the global climate events was confirmed by comparing the geochemistry of glass shards found in ice cores to that of the eruption deposits on Lombok. Search for geological evidence of these events was helped by many exposures and cross-sections of volcanic ash deposits which were caused by men bulk quarrying them for construction material. Climate effects. Ice cores in the northern and southern hemisphere display sulfate spikes associated with Samalas, the signal being the strongest in the southern hemisphere for the last 1,000 years, and being only exceeded by Laki's signal in the northern. In addition, ice cores from Illimani in Bolivia contain sulfate spikes from the eruption. For comparison, the 1991 eruption of Pinatubo ejected only about a tenth of Samalas sulfur. Sulfate deposition from the Samalas eruption has been noted at Svalbard in the fallout of sulfuric acid from the volcano may have directly affected peatlands in northern Sweden. The amount of released by the eruption has been estimated to be 158 million plus or minus. The mass release was increased in comparison with the Tambora eruption due to a more effective injection of tephra into the stratosphere and/or higher sulfur contents of the Samalas magma. When large-scale volcanic eruptions inject aerosols into the atmosphere, these can form stratospheric veils which reduce the amount of light reaching the surface. This reduces the temperatures on much of Earth, and can cause problems in agriculture including famine. However, social effects of such events is often reduced by the resilience of humans. Not all years, with cold summers are linked to volcanic activity. Volcanic eruptions can also deliver and into the stratosphere where they contribute to the breakdown of ozone. While most of these elements would have been removed by scavenging by the eruption column, the quantities that have been modeled for the Samalas halogen release would have reduced the stratospheric ozone. Samalas, along with the Kuwait eruption in the 1450s and Tambora in 1815, is one of the strongest cooling events in the last millennium, even more so than the peak Little Ice Age. The effects of the Samalas eruption form the strongest volcanic signal in boreholes of the Urals. After an early warm winter 1257–1258, winter warming is frequently observed after tropical volcanic eruptions, resulting in the early flowering of violets according to reports from France. European summers were colder after the eruption and winters were long and cold. Summer cooling reached 0.69 K change in the southern and 0.46 K change in the northern hemisphere. For comparison, the radiation forcing of Pinatubo's 1991 eruption was about 1/7 of that of the Samalas eruption. Sea surface temperatures likewise decreased by 0.3, triggering changes in the ocean circulations and the formation of deep water. Temperature changes may have lasted for a decade. Precipitation and evaporation both decreased as well, but the decrease of evaporation was stronger. However, the Samalas signal is only inconsistently reported from tree ring climate information, and the temperature effects were likewise limited, probably because the large sulfate output altered the average size of particles, and thus their radiation forcing. Climate modeling indicated that the Samalas eruption may have reduced global temperatures by approximately 2 C, change a value largely not replicated by proxy data. Better modeling indicated that the principal temperature anomaly occurred in 1258 and continued until 1261. Some climate models tend to assume that aerosol optical depth increases linearly with the quantity of erupted sulfur, and tend to thus overestimate the climate effects. The possible occurrence of an El Niño before the eruption may have further reduced the cooling. The Samalas eruption, together with another eruption in the 14th century, set off a growth of ice caps and sea ice, and glaciers in Norway advanced It might also have modified the North Atlantic Oscillation, causing it to acquire more negative values in the subsequent decades in cooperation with a beginning decrease in solar activity as part of the Wolf minimum in the solar cycle. The advances of ice after the Samalas eruption may have strengthened and prolonged the climate effects. Later volcanic activity in 1269, 1278 and 1286, and the effects of sea ice on the North Atlantic would have further contributed to ice expansion. The glacier advances triggered by the Samalas eruption are documented on Baffin Island, where vegetation killed by the advancing ice was conserved in it. Likewise, a change from a warm climate phase to a colder one in Arctic Canada coincides with the Samalas eruption. The Samalas eruption came after the medieval climate anomaly and at a time where a period of climate stability was ending, with prior eruptions in 1108, 1171, and 1230 already having upset global climate. Subsequent time periods displayed increased volcanic activity until the early 20th century. Indeed, the time period 1250–1300 was heavily disturbed by volcanic activity and is recorded by a moraine from a glacial advance on Disco Island, although the moraine may indicate a pre-Samalas cold spell. These volcanic disturbances, along with positive feedback effects from increased ice, may have started the Little Ice Age even without the need for changes in solar radiation, but this theory is controversial. The eruption left traces including decreased tree growth in Mongolia between 1258–1262 based on tree ring data, as well as a very wet monsoon in Vietnam. Another effect of the eruption-induced climate change may have been a brief decrease of atmospheric cooling may have lasted for 4 or 5 years based on simulations and tree ring data. Other regions such as Alaska were mostly unaffected. Likewise, there is little evidence that tree growth was affected in Fennoscandia, Quebec, and the western United States. In the case of Alaska, possibly the climate effect was moderated by the nearby ocean. Lombok Kingdom, Indonesia. This eruption led to global disaster in 1257–1258. The Babad Lombok describe how villages on Lombok were destroyed during the middle 13th century by ash and high-speed sweeps of gas and rocks. A kingdom on Lombok and its capital Pamatan were destroyed by the eruption and disappeared from history. Although the royal family survived according to the Javanese text, thousands of people died during the eruption. Bali and Lombok may have been depopulated by the eruption, possibly for generations, allowing Kertanegara to conquer Bali in 1284 with little resistance. Europe. Reports in 1258 in France and England indicate the presence of a dry fog, giving the impression of a persistent cloud cover to contemporary observers. Medieval chronicles say that in 1258 the summer was cold and rainy, resulting in floods and bad harvests, with cold lasting from February to June. In both Europe and the Middle East, changes in atmospheric colors, storms, cold and severe weather were reported in 1258–1259. In Europe, too much rain damaged crops and caused famines, followed by epidemics. Reports of the effects of the eruption, including failure of crops and famine, as well as weather changes, exist for Northwest Europe. Crop failures and a famine in London have been linked to this event. Witnesses reported a death toll of 15,000 to 20,000 in London. A mass burial of famine victims was found in the 1990s in the centre of London. Matthew Paris of St Albans retells how until mid-August in 1258, the weather alternated between cold and strong rain, causing high mortality. The resulting famine was severe enough that grain was imported from Germany and Holland. The price for cereal increased in Britain, France and Italy. Outbreaks of disease occurred during this time in the Middle East and England, with and after winter 1258-1259. Exceptional weathers were reported less commonly, but the winter 1260-1261 was very severe in Iceland, Italy and elsewhere. Byzantine Empire, Eastern Roman Empire. Potential long-term consequences of the eruption were the Byzantine Empire losing control over Western Anatolia, resulting from a shift in the political power from Byzantine farmers to mostly Turkoman pastoralists in the area. The origins of the Flagellanti movement may also be the social distress triggered by the eruption, but warfare and other plights may have contributed. Northeast Asia. Problems were also recorded in China, Japan and Korea. Other effects of the volcanic eruption include a total darkening of the moon in May 1258 during a lunar eclipse. Brought to you by WikiVidi.com. Would you like to know more?